Hello, everybody. So I'll say just a few words before we start. So it's a pleasure to have Professor Christoph Bohm here. I'll say a few words about him. So he got his diploma and PhD from the University of Augsburg, and the second under the guidance of Jost Heinrich Eschenburg. So he was a postdoctoral fellow for a couple of years at McMaster and got a DFG fellowship at Augsburg before becoming assistant at Kiel. Then he became active professor at Hamburg, and then he moved to Münster, first under the Heisenberg program, and then as professor. So he's a renowned expert in differential geometry. He had in particular fundamental contributions on Ricci flow, and I would like to mention his result with Wilking under curvature pinching conditions, leading eventually to the proof of the sphere theorem, as well as on the structure of Einstein manifolds. And the Einstein manifolds are precisely the content of today's talk. So let's welcome Professor Bohm.
Yeah, many thanks for invitation. Yeah, it's great pleasure and honor to be in Pisa and be allowed to speak here. So this is going to be a colloquium talk. Yeah. So if you know Riemannian geometry, I apologize. There will be some part you know very well. Yeah. But I do not assume you to know Riemannian geometry a lot. Yeah. And moreover, I mean, there are two approaches: a geometric one, yeah, and an analytic one. Yeah. And I will today take the more analytic side. Yeah. Even so, I consider myself a geometer. Huh? Okay, so in this talk, M and G is going to be a Riemannian manifold, yeah. So that means, of course, as you all will know, yeah, it's a smooth manifold of dimension n. Yeah, you can think about a flying carpet, yeah, such that each tangent space is equipped with a scalar product, yeah, GP, yeah. And the metric, so to speak, you may think of is a family of these scalar products, yeah, varying smoothly over the manifold, yeah. So in Rn, you could take an open subset, yeah, and you could take a family, yeah, of positive definite matrices, yeah, depending smoothly on the point, yeah. Okay, so as I say, I'm gonna take the analytic approach, yeah. So we can define immediately what the Ricci tensor is, yeah, of such an object, yeah. And I just learned this morning, yeah, that Ricci wrote his PhD thesis in Pisa exactly 150 years ago, yeah, 1875, yeah. And there's a trouble, yeah, and maybe we should be grateful, yeah, because the Ricci tensor is now called Ricci tensor, but it should be called Ricci-Curbastro tensor, yeah? Because that was the true name, and for some reason he skipped the second part. Yeah, it's interesting for historians why this happened. Well, nobody knows. At least I do not. Yeah. Okay. So what do you do? So you pick this point P. Yeah. So let E1, En be a GP orthonormal basis of TPMN. Yeah. And let V another vector, yeah, say, why not Swan, yeah? And then I'm going to give you a formula, and I have to apologize for giving a formula in a colloquium talk after 2 minutes, yeah? It's in some sense a crazy thing to do, yeah? There will be excuses to do this, yeah? Okay, so the Ricci G, yeah, in the point P, applied to the vector VV, well, is a sum I is 1 to n, GP, yeah, nabla, V. Yeah, so the precise formula is not going to be important, yeah. I will tell you what's important, yeah, and what you should take away. So first, there's a little of cheating, yeah. So these are local extensions, yeah, of these vectors, yeah, and the result you can check does not depend. You see there's an average, yeah, I could and maybe should have told you what's the Riemann curvature tensor, because Bernhard Riemann was German after all, yeah. But I will not, yeah, I will not. So, but what are these guys here, yeah? If you don't know, yeah. So now, if your manifold happens to be, yeah, Rn with a standard metric, so meaning you're in first year calculus course, yeah, then in this case, the nabla Wx, which I would like to consider as W dot X applied to W, so this is going to be an endomorphism of the tension field, yeah, is nothing but the Jacobian, yeah, yeah, in Rn, yeah. So this is what this is, and now I have not told you what this is. Well, that's a Levi-Civita connection of that Riemannian manifold, yeah. So what do you know in calculus 1? How to differentiate vector fields, yeah? Maps from Rn to Rn, yeah. So that you can do on a Riemannian manifold is not unique anymore, yeah. But there's a new unique choice, yeah. And then this is now called the Levi-Civita connection, and this is what this nabla is, yeah. And I mentioned this because, well, Tullio Levi-Civita was, I guess, a student of Ricci, yeah, and maybe even the most famous one, to put this carefully, yeah. Okay, yeah, this will show up later, yeah. So this is an endomorphism, yeah, like the differential, yeah, of a vector field is an endomorphism, yeah. So it has a trace, for instance, and so on, yeah. Okay, key point, second derivatives, yeah. You differentiate once and another time, yeah. So second derivatives go in. You could use local coordinate vector fields, yeah. You would get the formula, wouldn't tell you anything if you don't know, yeah. It's a horrible formula, yeah. And in some sense, you see, there's an anti-symmetrization, yeah. So you ask how much do taking first order derivatives, how much does that compute, yeah. On Rn, you would check, well, these terms are all zero, yeah. Yeah, they would be dead zero, yeah. So this would be dead zero, yeah, on Rn, yeah. And always a flat metric, yeah. So saying calculus 1, yeah. Now, yeah, second definition. We can already define what's an Einstein metric, yeah. Yeah. Einstein metric. Yeah, so a Riemannian manifold, M and G, is called Einstein if there exists a number lambda and R, the Einstein constant, yeah, such that the Ricci tensor, yeah, I didn't tell you, but you can check. So this is a quadratic form, yeah, it scales correctly, yeah. So this is, you can extend it to a symmetric bilinear form, yeah, on the tension bundle, yeah. So you can plug in V1, V2, and you can flip, yeah. But the metric itself is a symmetric bilinear form, and you ask, well, when is that true, yeah? Yeah. When is the Ricci 2 form a multiple of the metric itself, yeah? I will make 5 comments on this. Before doing so, in certain coordinates, you may think about this as -1/2 Laplacian of G plus lower order terms. Yeah, I will not say more about this. You can take this, if you like, symbolic. Now, you may, in your head, I'm not going to do this for you, yeah, replace the metric G, which is a tensor, yeah, by a function and ignore the lower order terms, and then assume the manifold being compact and do a partial integration, yeah, finding, well, in such situation, the lambda had to be bigger or equal than 0, yeah, being 0, well, if and only if the function would be constant, yeah. So also explain that I take the wrong definition, the wrong sign, yeah, I apologize for the Laplace, it's a negative operator, yeah, it's a trace of the Hessian, yeah. Okay, now let me come to my comments, yeah, before I go a little deeper into this, yeah. I mean, the term, of course, comes from general relativity, yeah. And there one considers not Riemannian metrics, but Lorentzian metrics, yeah, like G minus the t squared plus the x squared plus the y squared plus the z squared, yeah, on R4, this one, yeah. So of course then, you know, there are vectors which are not zero, but which have length zero, yeah. In the remaining case, this cannot happen, yeah. Of course, a vector which is not zero, it's a scalar product, will have positive lengths, yeah. Yeah, using a symmetry ansatz, there were famous explicit solutions, yeah, by Schwarzschild, yeah, around 1915, and then more channeled by Kerr around 1963. Yeah, modeling black holes, yeah, in the first case, which are not rotating, and in the second case, rotating black holes, yeah. So now I learned from the physicists, yeah, they really check, yeah, so they see the black holes, yeah, and they determine, yeah, the mass and the rotation speed, yeah. So they can say most likely it should be this and this, yeah. And here I would like to point out, I have a colleague in Münster, Gustav Holzegel, and he is an expert on the stability of the Kerr metric, yeah. So a question in physics always is, how stable is an object, yeah. So in this situation, the question is, you have this explicit solution, the Kerr metric, yeah, and somebody touches this, yeah, slightly disturbs it, yeah. So the question is, what happens over time? Yeah, is there chaos, or do you see after a long time one of the Kerr metrics again? Yeah. So these are very, very deep questions. Yeah, that's which only have been solved recently. Yeah. So if you want to learn more, he is one expert on this. When did I start, Andrea? Four, 8. Okay. Yeah, let me come back to Riemannian geometry. Yeah, the next observation is trivial. Yeah, can assume lambda -1, 0 +1. Yeah, so there's a rescaling thing. Yeah, you make a sphere, a small sphere, a big sphere, and whatsoever. Yeah, so it what only matters is the sign. Yeah, a third remark. Yeah, for M n compact n bigger or equal than 3, Einstein matrix G are critical points of the so-called Einstein-Hilbert action, yeah, or the total scalar curvature function, which is S M1, space of all Riemannian matrix of volume 1, yeah, to R, assigning G the scalar curvature, yeah, integrated against the volume density. If the manifold is orientable, yeah, would be the volume form. And what is this? Well, this is trace G, rich G, yeah. So it's not an endomorphism that has a trace. It's a two form, yeah. You need to say which trace you take, yeah, and you take it, you plug in an orthonormal basis, yeah. Now this sounds like great, yeah. It's an Euler-Lagrange equation, so to speak, yeah, the Einstein equation, yeah. But unfortunately, so far, yeah, this was not so successful. I mean, there are not really, as far as I know, yeah, many applications, yeah, using this, yeah, and there are two reasons for this. This functional is neither bounded from above nor below, yeah. You cannot take minimizing sequences or maximizing sequences. Huh? And then even worse, if you wanted to apply a mountain path lemma, yeah, there's no good compactness, yeah. There's no Pauli-Smee condition known, yeah, whatsoever, yeah. So it's so far, yeah, this seems very, very tempting, yeah, to use this, but okay, but and I should mention something what gives me the opportunity to mention another geometer, Riemannian geometer, so to speak, as we would say from Pisa, Bianchi. Yeah, he made the PhD in 1877. Yeah, 2 years after. And he's known for the Bianchi identities. And this is like the key thing here, because you should be completely surprised by what I said. Why? Now, the scalar curvature is an operator has second order derivatives. Yeah. Now, if you compute the Euler-Lagrange equation, you expect third order derivatives. Yeah. Clearly, yeah. Like you take the Dirichlet energy, first order, and the Euler-Lagrange is second. Yeah. But here, not. Yeah. The Euler-Lagrange is also second order. Yeah. And the reason is that the second Bianchi identity. Yeah. So, okay. So that's another remark. Okay. Oh, I have time. Maybe, yeah, low dimensions. Low dimensions. So linear algebra will give two things in dimension n equals 2, 3. Yeah, if you have an Einstein metric. So this implies the sectional curvature is constant. I have not defined what the Riemann section curvature is. Yeah, some, so to speak, well, a similar thing here without summation. Yeah, but I'm going to tell you, well, what are the Riemannian manifolds, the complete ones with constant sectional curvature? That's easy. Yeah, so this is either the round sphere, Sn, yeah, of a certain radius, yeah, or flat Euclidean space, Rn, or, well, hyperbolic space. Yeah. So they have constant section curvature, and I did not tell you precisely, this is an averaging process. Yeah. The Ricci will be constant for trivial reasons, so to speak. So these are examples of Einstein metrics, but they are trivial ones, yeah, and they are not of interest, so to speak. Yeah. At least if you go to the universal covering. Yeah. So whatever you want to. So the story really starts in dimension 4, yeah, which is for many reasons maybe the most interesting dimension, as I will point out in a second, from geometry and also topology. Yeah. And one reason is that, again, the linear algebra tells you, yeah, the Lie algebra, meaning the tangent space of the special orthogonal group, yeah, in the identity. Well, this is not a simple Lie group anymore in dimension 4, yeah, but it's SO3 plus, SO3 minus, simply caused by the fact that left multiplications by unit quaternions on R4 are isometry, and right multiplication by unit quaternions on R4 are isometries. Well, left and right, they commute, of course, yeah. So this is not a simple Lie group, this is a splitting, yeah. And this has tremendous impact, yeah, for orientable manifolds in dimension 4. Yeah? Many things you can do there, you cannot do in higher dimensions for this simple reason, yeah. For instance, here you get obstructions, yeah. You get easy obstructions to the existence of Einstein metrics. On orientable M4, yeah, relating the Euler characteristic and the signature, yeah, it's called the Hitchin-Sob inequality. I will not go more into this, yeah. I mean, it's clear, yeah. So on this you can give a colloquium talk, yeah. On that you can give a colloquium talk, and there will be more topics, yeah. You can give an entire talk, yeah. Okay, so this is yeah, first part, yeah, of my talk, so to speak, yeah, an introduction. So yeah, we think about this as an elliptic equation, yeah. It's not quite true, yeah. It's weakly elliptic, yeah. There's a diffeomorphism group acting on solutions, yeah. They come always in infinite dimensional families, yeah, causing analytic trouble, yeah. And yeah, in the second part of my talk, I would like to speak about known examples, yeah. And here I would like to focus on the case that the manifold is compact, yeah? Of course. There are two cases, the manifold is compact, and then we would like to have some completeness, yeah? I will not say what that is, yeah? Or, well, it's compact and completeness is no boundary, yeah? Then completeness is granted, yeah? And kind of the reason is, well, since this is kind of elliptic equation, you expect a maximum principle, so that means on a compact manifold, you expect it to be more difficult, yeah? To solve that equation, yeah? Compared to a non-compact manifold, yeah? So say on C, R2, you have many holomorphic functions, yeah? The real part is a harmonic function, yeah? So there are many, yeah? But if you say on S2, how many functions are on S2 to R, yeah? There are not so many, yeah? So, yeah, this becomes very restrictive, yeah? So the compact part is, even so, of course, the non-compact part is studied as well, yeah? Okay, now for a while, let M be compact. Yeah. Yeah, so let me make a little sense of this, yeah? Let me give you a second formula, yeah, which is again not terribly important, but which I like a lot. So we integrate over the manifold this 2 form, and here I plugged in only vectors at a point, but I can plug in vector fields, yeah? Now this is a real number. This is a smooth function on the manifold. I integrate it against volume density, and then I give you a formula, yeah? So there are second order derivatives, yeah? Nabla, nabla. And you do a partial integration. I'm not going to do this, yeah? And what you get is the trace of this endomorphism squared, yeah? So this is nothing but the divergence of x plus minus 1, depending on your convention, yeah? Minus the trace yeah? So this is a well-known formula, yeah? I would like to stress, yeah? I did not tell you what the nabla x is, yeah? Is something like the differential of x. So this is first order. So this is quadratic, yeah? But first order. This is also first order, yeah? So there are no second derivatives anymore, yeah? So you have an expression, yeah, where only first order terms appear, yeah? Okay, yeah, it's for various reasons. I like this a lot. I guess it has not been used a lot, yeah? This formula, yeah? Now, let me give you 2 examples, yeah, to warm up a little with that formula, yeah? So the vector field x on Mn is called killing. Yeah, he was a mathematician, yeah. It's not going to kill you, yeah. If and only if this endomorphism, the transpose with respect to G, is minus this endomorphism, yeah. In other words, it's Q-symmetric with respect to G. Yeah? This is equivalent to the fact, yeah, that the flow consists of isometries, yeah, of the underlying manifold, yeah. And now you can say, suppose I have such a thing, yeah. You look at the formula, yeah, and then you check, well, minus nabla x is nabla x transpose. So you have trace nabla x transpose nabla x. That's the norm of nabla x squared, yeah. So it's bigger or equal than 0. This is a square bigger or equal than 0. You see the right hand side is bigger or equal to 0. So that means the left hand side must be bigger or equal to 0, yeah. It's telling you that if you have a Riemannian manifold, a compact one with negative Ricci, yeah, where this thing is negative, yeah, you cannot have killing fields, yeah. It's impossible, yeah. So that's one thing. And another thing is, so to speak, the opposite, yeah, is a local gradient vector field. Well, if and only if, well, this endomorphism is self-adjoint, yeah. Yep. Well, if you have a killing field, yeah, the right-hand side is non-negative. Therefore, the left-hand side is non-negative. So by contrast, if you would have a compact Riemannian manifold such that the Ricci G, say is minus G, is negative definite, yeah, is impossible, yeah? Yeah, so that means these manifolds do not have any symmetry, yeah? You can't use symmetries to create such examples, yeah? So this is what this formula is, a one-line proof, yeah? The normal proof is different, yeah? There are other proofs, but, well, I mean, why not use this formula, yeah? Okay. Yeah, of course, it's clearly not true, yeah, that any vector field, yeah, is a sum of a killing field and a local gradient, yeah. Something similar is true, yeah. You have the Hodge decomposition or Helmholtz decomposition, yeah, but not this one, of course, yeah. Okay, so yeah, so this is the Einstein equation, yeah. So let me warm out a little bit and remind you. Well, you won't like to have Ricci G is minus G or Ricci G is plus G, yeah? So what about, yeah, positive Ricci or negative Ricci, yeah? I mean, how much is known and what can we say, yeah? So what about Ricci G less 0? Yeah. Yeah. Well, so there it's known for n bigger or equal to 3, there is no obstruction, yeah? Yeah, by Loukamp. Yeah, any compact manifold of dimension bigger or equal than 3 has a Riemannian matrix of negative Ricci, yeah? And there are many, yeah. I guess they are dense in C1, yeah. So I mean there are really many, yeah. So okay. However, so maybe I do not write this, but only tell you this, yeah. A natural question was, yeah, what about Ricci G almost minus G, yeah? Using those methods, yeah. So he can show that on a certain, yeah, you can have Ricci bounds, reaches between is minus a and minus b, and yeah, such a thing can be proved for universal constant. But then the next question, maybe you can improve, yeah, the methods to almost constant, yeah, not quite constant. That's a different issue, but almost, yeah. So apparently, this is difficult or even impossible using those methods, yeah. So that's not clear, yeah. How to upgrade, yeah. But in itself would be a very interesting question, yeah. Can you create, yeah, is there a method to creating almost Einstein metrics with negative Ricci curvature? So far, it's not known, yeah. Okay, so here, almost no obstruction, yeah. Now, what about the opposite? Well, there are several things known, yeah, and it's much more obstructed, yeah. The first thing is the fundamental group is finite, yeah, by Boni-Myers, yeah, that's easy to see. Then, of course, if the Ricci is positive and you take the trace, yeah, the scalar curvature is positive. And that implies obstructions, yeah, say on spin manifolds or non-simply connected manifolds, yeah, I will not go into this, yeah, there are obstructions. And then there should be conjectured more obstructions, yeah. Yeah, it's not believed, yeah, that any manifold which admits a metric with positive scalar curvature admits and has finite fundamental group, yeah, or simply connected admits a metric with positive Ricci, yeah. This is much stronger, yeah, than that, yeah. There's an averaging again, yeah. Okay, so from this point of view, you would think it should be very hard to construct Einstein matrix with positive Einstein constant, and it should be very easy to construct Einstein matrix with negative Einstein constant. Yeah? The examples we have are the opposite, yeah? In a drastic way. Yeah? It's just what it is. Yeah. So one can speculate on this. Yeah. But this is as I will come now to the examples. Yeah. And okay. So what do we know? Except the Kähler case. Yeah. That's special. Okay. Now examples. Yeah. Maybe the most important class are Kähler manifolds. So Kähler-Einstein. Yeah, these are even dimensional Riemann manifolds, yeah, such that there's a complex structure in J, meaning, yeah, J squared is minus identity. It's integrable, yeah, there's some condition, and it's even parallel, yeah. Yeah, so lots of structure, and the lambda could be -1, 0, 1, yeah. So -1 was dealt with first, yeah, 0 was a Fields medal, yeah, and the +1, it took about 30 years to handle this, yeah. I will not go into this at all. Another talk, maybe 2 or 3, yeah, even on this, yeah. I have another colleague in Münster, Hans-Joachim Hein, yeah, he is expert on this, yeah. Kähler-Einstein manifolds, also gluing constructions, yeah. So that's like, but I will not go into this, yeah. Now there is an odd-dimensional analog of this, yeah. You see, they're all even dimensional. So these are called Sasaki Einstein manifolds. M to n plus 1 G, yeah? And Sasaki can be easily explained. Sasaki just means if you have the cone, dt squared plus t squared G, yeah? So this is scalar. Yeah. And again, this is a whole story, yeah, in itself. You could give a colloquium just on this, yeah? Let me just get you a glimpse, yeah? Yeah, on S to n plus 1, there exist infinitely many families of Sasaki Einstein matrix. Yeah, they always have to be positive Einstein constant, yeah? For all n. Yeah, so starting with S5, yeah? S5, S7, and so on, yeah? Even exotic spheres, high dimensional families. So, I mean, they exist in abundance, yeah? I mean, there's a huge universe, yeah? and what we expected, the opposite, yeah? But yeah. Okay. Yeah, so these were even dimensional spheres, yeah? Now, I guess it was an old question of Marcel Berger, yeah? What about odd dimensional spheres? Yeah, if I say Einstein matrix, of course, on spheres, I mean always non-trivial ones, yeah? There's always the round metric, yeah? But that's boring, yeah? So all these metrics are not round, yeah? So they look different, yeah? Okay, so this is what will be also my last part, yeah? So there's a what I will call symmetry ansatz. Yeah, and that gives you that on S6, S8, S10, and S12, there exist Einstein matrix. Yeah, it's lambda bigger 0. Yeah, I mean non-trivial ones. Yeah, and here let me give some names. So I myself did this, maybe started this 98. Then there's Lorenzo Foscolo. I guess he's now in Rome, I guess. Yeah, you move back to Haskins. 17. And then quite some. So this was a 6, S8. This is a 6, a nearly Kähler one. Then there is Nienhaus Wink, S10, 24. Then another one on S8. And then on S12, Buttsworth and Hodgkinson. Yeah. But well, so it's unclear, yeah. But it should be, of course, that you would find those guys in all dimensions, yeah. But the answer seems to be, yeah. But I will come to this a little in more detail, yeah. Okay, so this is lambda positive, all lambda, yeah. Now my third class of examples are, yeah, holonomy G2 and spin 7. For dimension n is 7 and n is 8, yeah. And here I should, of course, Dominic Joyce and many others, yeah. I'm sorry, I cannot give credit to all, yeah, people working on these things, yeah. Sasaki, I did not mention any, yeah. Boyer, Garlitsky, Kolar should be mentioned, of course, yeah, but many others should be, and Kähler, that's clearly impossible to do this. Here, similar story, yeah. So the special thing here is like you don't have to deal with a second order PDE, you can deal with a first order PDE, yeah. But there are also gluing methods, and there's still very interesting open questions, yeah. For these Ricci flat manifolds. Yeah, so this is lambda 0. Sorry, I should have said this. This is lambda 0. Yeah. And now the negative side, yeah. So it's this side, yeah, where we expected, yeah, to find many examples. This is where we have the least, yeah. Yeah, so there's a gluing constructions, yeah. Yeah, and there are 2 papers I'm aware of, yeah. So n is 4 by fine Sposimelli, 20, yeah. And now n bigger equal than 4 by Harmenstedt and Frieder Jäckel, yeah. And I mean, you start with a metric which has almost constant negative curvature -1, almost, yeah. It's not homotopy equivalent to a hyperbolic manifold, but almost, yeah. And then you still can kind of do a gluing method, meaning that you can, yeah, if you want to apply the implicit function theorem, yeah, you need to get hands on the linearization, yeah. And then, of course, it's very helpful to know that the sectional curvature is almost -1, yeah. This is key, yeah. But so far, yeah, of course, these guys, since they have originally negative sectional curvature, the fundamental group is huge, yeah. Yeah, it's not like they cannot never be simply connected. Yeah, the universal covering spaces are Rn. Yeah. Yeah. So here's one question. Yeah, I do not know. Yeah. So construct a problem. Yeah, construct compact one connected Einstein manifolds. M and G with lambda -1. Yeah. One connected. Yeah. We know them. Yeah, which are not Kähler. Yeah. I do not know such an example. Maybe, yeah. Okay, so that's completely striking, yeah. Considering this result of Lohkamp saying negative Ricci is no condition whatsoever. You find these metrics, you find them in abundance. I mean, it's a huge family, but somehow you cannot make the Ricci constant. Yeah? It's a PD problem. Yeah? Okay.
Sorry, Pine Tomaselli and Hammerstedt Jekyll. So they started with, say, two constant curvature manifolds, and they glue them to
No.
Einstein. Or...
No. There are, that's an old result by Gromov and Farrell maybe. There are manifolds which admit Riemannian metrics with are pinched between 1 minus epsilon and 1 plus epsilon. Almost constant negative section curvature. However, which are not homotopy equivalent to hyperbolic space. Yeah. And these are the ones they take. Yeah. I mean, you want to be sure afterwards, so to speak, that you do not get a hyperbolic manifold. Yeah. Because that will be known. Yeah. So that's then it would still be interesting. Maybe another metric. Yeah. But you want to be sure. Yeah. So and then they do some gluing. Yeah. So no, they do not start with. Yeah. Okay. Yes. That goes in the same. I guess Anderson first, yeah, and then Bamler, yeah, yes, yeah. That's very yeah, yes. Yeah. But again, the fundamental group is huge, yeah, with these examples, yeah. So it's like, yeah, why? I mean, yeah, S4. Yeah, find an Einstein metric on S4 with negative reach, yeah. Okay. But any is simply connected with two, yeah. So they're just not, I don't know any methods, yeah. Okay, so in the remaining, say 15 minutes, yeah. So this is a little striking, yeah, as I say. So we expect a certain behavior, but then if it comes to examples, yeah, if you disregard the Kähler case, yeah, of course, there are many with negative and zero, yeah, there you have, but if you do disregard this, yeah, it's so to speak, it's the opposite, yeah. It's more like, yeah, this baby question I told you, yeah, if you replace the G by an F, yeah, and ask what should be the lambda, yeah, then this analogy would be for non-negative Ricci, yeah, for Einstein, yeah. But yeah, many people, of course, believe that there should be plenty, yeah. Okay. Yeah, so the last part is, I guess, yeah, something what people, of course, try if we cannot prove a theorem without any assumptions, yeah. They make assumptions, yeah. I mean, Kähler, Sasaki is one assumption, yeah. Clearly, yeah, special anomaly G2 spin 7 would be another assumption, yeah. There's a third kind of assumption I have not speaking about, yeah, but I will speak about, yeah, the symmetry answers, yeah. Yeah, you assume, like in physics, yeah, the Schwarzschild, yeah, there's a group acting, yeah, such that the orbits have codimension 1 or hypersurfaces, yeah. For the Kerr matrix, yeah, well, there's a group acting, indeed, yeah, two-dimensional abelian group, such that the orbits are two-dimensional, yeah, in this four-dimensional space-time, yeah. So well, people do these things and get interesting examples, yeah, and sometimes you can learn something from it, yeah. Well, sometimes it's of course special to this ansatz, yeah. So the most, yeah, symmetric ansatz is, well, so a Riemannian manifold G is called homogeneous space, yeah. If the isometry group, yeah, that's a D group, acts transitively, yeah, on the manifold, yeah. Yeah, in some sense, these are boring manifolds, if you like, yeah, because if you're at point A or B, yeah, you cannot distinguish, yeah. It looks alike, yeah. It's not like Florence and Pisa. There's the C and there are Monte Morello, yeah. No, it looks alike, yeah. But still, of course, you can ask, yeah, what can we do? And of course, since you assume so much symmetry, so this is an algebraic equation, yeah. I'm sorry to say this here, yeah. There's a hierarchy, of course, yeah. If the isometry acts like with codimension 1 orbits, then the Einstein equation becomes a dynamical system in ODE, yeah. If, like in the Kerr metric, yeah, the isometry group acts with orbits of codimension 2 or smaller, yeah, then it's a true PDE, yeah. But only in 2 variables on the orbit space, so to speak, yeah. Here the orbit space is 0-dimensional. In the next example, it will be 1-dimensional, yeah, and then 2-dimensional, yeah. So you may ask, well, maybe you can say more, and maybe this is helpful, yeah, also getting ideas for the general problem, yeah. I mean, there are results, but yeah, so far did not help to tackle the general problem, yeah. So let me give two examples, yeah. There's a Wahn theorem I proved recently. Yeah, so if you have a homogeneous Einstein space, Einstein manifold, M and G, with negative Ricci, is a Euclidean space. Mn is diffeomorphic to Rn, yeah? Yeah, so this is, I mean, it's a tremendous abstraction, yeah? So that means only a contractible homogeneous space, yeah, admits such an Einstein metric. As soon as there's topology of any kind, fundamental group or whatsoever, yeah, you could take, I mean, an example for a non-compact homogeneous space would be S2 cross R, S2 cross R2, SL3R, yeah, SLNR, yeah. There are many, yeah. But only one of them, yeah, topologically allows Einstein, homogeneous Einstein matrix of negative energy. So this is like, yeah, this is like more like, again, against this, yeah. So there are theorems along, yeah, which make much less assumptions on symmetry, yeah, and giving you results like, yeah, there are metrics of negative Ricci in that class, but you cannot improve to Einstein, yeah. So there exists system, but always assuming some symmetry, yeah. Now let me tell you, even so, yeah, this is an algebraic equation, yeah. We do not have an algebraic proof, yeah. And none of the results, unfortunately, we do have algebraic proofs, yeah, which is unfortunate because it would kind of explain the algebraic structure maybe also of the PDE, yeah. So we use even PDEs, yeah, to prove that this algebraic equation does not have real solutions, yeah. So it's difficult, yeah. Another thing, you know, I have 50 minutes, so I have 5 minutes. Okay, so let me state this, yeah. So this is classic. Ksevsky. Yeah, so it's homogeneous plus Ricci flat implies flat. Yeah. There's a very easy proof. I will not give it to you. I'm sorry. Would be a little geometric, yeah. But the true proof is unknown. Yeah. There should be an algebraic proof. Yeah. So the Ricci is an algebraic object. It's a symmetric, yeah, n by n matrix. You can think about it like this. Yeah. It vanishes, and then you should kind of be clever, get clever estimates. Yeah. Getting hands on the largest eigenvalue of the symmetric n by n or the smallest ones. Yeah. And then prove, well, something must vanish more than you expected, and not only the Ricci vanishes, but the full curvature tensor vanishes. Yeah. So this problem is open for 50 years. Yeah. Nobody has any clue how to get hands on this, and this is a problem because that means, well, we cannot, if you can not solve this algebraically, you are stuck with, yeah, if you assume less, yeah, then, well, on the orbits, these things will show up, yeah, and if you cannot handle them algebraically, yeah, you are in trouble, yeah. So maybe we never ask analysts, yeah, because they would not be interested in such a question, yeah. But it is actually, it's estimates, yeah. You would need really sophisticated estimates, yeah, to prove this, yeah. But as I say, it's considered to be extremely difficult, yeah. Of course, there are examples known, yeah, where this can go to zero, yeah, just to warn you, yeah. You can let this go to zero, yeah, but you never make it, yeah. So you have to prove that this, so it is subtle, yeah. You know, geometrically, yeah, you can write immediately, you can write down. So you take an S3, yeah, you take the Hopf fibrillation, you shrink the S1, yeah, you collapse, yeah, so the curvature will go to zero. Therefore, the Ricci will go to zero, yeah. But of course, on S3, you cannot have a Ricci flat metric, which would be flat. Yeah, that's impossible. Yeah? So I mean, it is subtle. Yeah, it is really subtle. But yeah, it would be great. Okay, maybe I skip the positive ones. There are also general structure theorems, yeah, for Einstein manifolds of positive Einstein constants. They are good enough to get a picture in low dimensions, yeah, dimension up to 12. So there you can classify, so to speak, yeah, which homogeneous, compact homogeneous spaces do admit homogeneous Einstein metrics and which one not, yeah. But in higher dimensions, the picture is still open, yeah. It's not clear, do most compact homogeneous spaces admit an Einstein metric, a homogeneous one, or not, yeah. It's completely open, yeah. So this, so to speak, some people would consider a classification, yeah. It's not quite true. There are some subtleties I will not speak about, yeah. But topologically, it's a classification, yeah. That's it, yeah. Of course, that's as well. The flat ones, yeah, they're covered by a flat Rn, yeah. But on the positive side, yeah, is yeah, maybe this is a little bit similar to the Kähler case, yeah. There, of course, negative side was the easiest one, yeah. The Ricci flat one was, yeah, was much more difficult, but still kind of, I'd say, I dare saying easy compared to the positive case, yeah, which is much, much harder, yeah. Okay. Yeah, so this is a level 0, so to speak, yeah. And then the next level is, well, you drop, yeah, a little bit. Yeah, so Riemann manifold M and G is called G Geneity 1 manifold if G symmetric group acts with codimension 1 orbits, yeah. Yeah, so the picture you should have in mind. Yeah, for n is 2, is a surface of revolution. Yeah. Yeah, S1 is acting on S2 by rotation, yeah. The principal orbits are S1, and there's a north and a south pole. Yeah, it can happen that there are orbits of lower dimension. Yeah, this can happen. Yeah, and there's of course a map. And the most interesting part is when this is an interval. Yeah, the orbit space is an interval, like for the round S2. Yeah, but there are many more examples. Yeah, and in this case, yeah, so a metric G, you can write if you follow a normal geodesic. Yeah. You can write as dt squared plus g of t, yeah, and there's a principal orbit p, t, yeah, and this is a family of homogeneous matrix on this principal orbit PT, yeah, which is of course in itself a compact homogeneous space, yeah. And then the Einstein equation becomes a singular ODE, yeah, of second order, yeah. I will not give you the formulas, yeah. So this is a little more interesting, of course, yeah. And then kind of what you want is, yeah, what people try. Maybe I only say this, yeah. I mean, there's yeah, there exists yeah, I mean, so globally Mn minus, Mn plus, yeah. And if these guys are Q minus and these are Q plus, yeah, then this is a disk bundle over Q minus, yeah. In this case, it's just a two-disk, yeah, two-dimensional disk, yeah, it's 1 point. But in general, the picture looks like this, yeah. It's like that's Q minus, yeah. And the PTs, yeah, you should think about as distance tubes, yeah, is something like R cross S1, yeah, and collapsing to R, yeah, generalizations of this, yeah. So the boundary would be the PTs, yeah, at the different radius, yeah, and here the core, so to speak, is something lower dimensional, yeah. Now this is one side. On the other side, you have the same thing. You glue it together, yeah, and here, yeah, you have existence of G invariant Einstein matrix on Mn minus, yeah, which are not complete, yeah. So you can do a power series ansatz, yeah. So the issue is, let me just say briefly, last minute, what the issue is. So it's like polar coordinates on R2, yeah. It's nice to have them, and if something is invariant, yeah, on a rotation on R2, yeah, you're gonna use it. But what sometimes happens, you create a coordinate singularity, yeah. It's not a singularity, but the price to pay for picking the nice coordinates is that some ODE or PDE becomes singular, yeah. This is what happens here, yeah. So this is a singular PDE if you come to this. But of course, you wanna have a invariant Einstein metric which can be extended smoothly, yeah, to the singular orbit, yeah, on R2 to this point, yeah. You want this, yeah. And there's quite well developed theory, yeah. So this is my advisor back in the time, Eschenburg, Wang, yeah. I guess they started this. This was around 2000, and now Verdiani, yeah, and Ziller, very recent, yeah, generalizing this, yeah. So you have them here locally, yeah, on a small neighborhood, yeah. More you don't know. And then what you try is what all these people tried, yeah, on S6, S8, S10, and so on, and many other examples in the compact case. Well, you try to prove that some of them close up smoothly, yeah. Yeah, and it's similar like finding for an ODE a periodic solution, yeah. So this is similar in nature. You should think about this, yeah. What I'm saying is non-trivial, yeah. It's like a heteroclinic solution, yeah, between two zeros, yeah. So this is like on the difficulty, but as I say, well, it's even more difficult because you have singularities here and here, yeah. So you shoot into the singularity, so to speak, and it's non-trivial, yeah. So you want to extend that, yeah. So this local theory is well developed, yeah. You have them, they exist. I mean, but then the closing up, yeah, there are theorems. I will not address them now, yeah. But there's no general theorem, yeah, saying like under this and this assumption, yeah, you're gonna find one which closes up, yeah. And there are still work to do, yeah, and there are first results, but because of time, let me skip them, yeah. And maybe it's a good time to stop.
Do we have any more questions? I have a couple, actually. I presume the answer is no, but I suppose on exotic spheres, is there any known Einstein
Yes,
symmetry?
yes. The Sasaki ones, they exist even, they can show on dimension 7 on all exotic ones, yeah.
Yes.
So I mean, this machine is really powerful, yeah. So yeah, the symmetry ansatz is not known, yeah. There exist Cohen-Gini 1 actions on a few exotic spheres, yeah. So theoretically, that would be possible, but yeah, as I say, I mean, the ODEs one can deal with so far to get compact examples, yeah, are very low dimensional, yeah. It's very limited methods, yeah. So I mean, one should have, yeah, there should be much more, yeah. In the non-compact case, yeah, again, you see, if there's only one single orbit, yeah, the non-compact case, yeah, so there's nothing like this, yeah. You want to show that these solutions exist for all times, yeah. So this is lambda 0 or lambda is negative. Things become much easier, yeah. And there are many examples, yeah, important ones, yeah, like Ikushi-Hansen, like many, yeah, high dimensional families whatsoever, yeah, but not, yeah. In the compact case is again, you see, this closing up makes things so difficult, yeah. Living forever is much easier to show, yeah. No, yeah, but they exist, yeah. You have them even on exotic spheres, yeah. And in families, even families, yeah. I mean, it's like.
Then I have like a curiosity, maybe kind of unrelated. I mean, partially unrelated. Say, compact manifold, you can always isommetrically embed in some Euclidean space. If you know it is Einstein, maybe does the embedding become special? Can you maybe lower the dimension, or so? Do you know of any? I mean, how if the Einstein condition can help, like embedding?
I don't. I mean, honest answer, I don't know. Yeah. I also would not. I mean, it would be surprising if this would help. Yeah, but I do not.
And sorry, I actually have a third question. In your work with Ramiro on homogeneous manifolds, so you said in principle, I mean, there could be an algebraic proof, but use like more PDE methods. Is that like some decay or a Liouville theorem? I mean, what kind of PDE? I mean, just.
I mean, this is a long paper and it's very. I mean, we give away symmetry, yeah. So if they're homogeneous, you think you want to have this, yeah, but this is not what we do. We find special subgroups of the isometry group, yeah. I mean, certain nilpotent Lie groups, they act nicely, yeah, and those we take, yeah. This is like we give away symmetry at the so to speak that's a cost, but the gain is like the group acting now with very low homogeneity, yeah, is nicer, yeah, and that we use to get obstructions, yeah. But then yeah. I mean, you at some point and the best way to say this, at some point you need kind of an ODE. You would say you would need an integrating factor for this ODE, yeah. And now there's a PDE, and so to speak, you need an integrating factor for that PDE for certain estimates to work, yeah. The remaining submersions, I mean, I cannot, yeah, it's a 60-page paper, yeah, and then it's using many things, yeah. Maybe the interesting thing is, or what I think is much more interesting, I mean, as I say, there are non-existence results which are much more general, yeah, which have a assumption like, yeah, or I mean, the orbits are like, yeah, whatever, yeah, like one-dimensional only, yeah. So very mild symmetry assumption, and you still get obstructions, yeah, but only if the Einstein constant is negative, yeah. So these obstructions would give you nothing in the positive case, yeah. So this kind of fits well with this picture, yeah, at the very beginning, yeah, that the Ricci is -1/2 Laplacian f, yeah, is like, so to speak, and then you should have no problems with lambda bigger or equal than 0, but you should get problems with lambda less than 0, yeah. under this assumption. Yeah. Still, there's a low count result, yeah, telling you negative Ricci. So yeah, it's yeah. Yeah, no, I mean, you as I say, this would be, of course, fantastic. I mean, it is extremely expensive, yeah, to get to. I mean, we show an algebraic equation has no real solutions, yeah, by doing crazy stuff, yeah, Riemannian submersions and whatever, yeah, to get hands on this, because we cannot solve the algebraic equation, yeah. I mean, the algebraic equation, for maybe for the specialists, there are real solutions, yeah, to these algebraic equations, yeah, but they are not Riemannian, yeah, they're semi-Riemannian, yeah. Yeah, so you cannot even show, well, use maybe some algebra saying, well, this real solution, make it, are there any complex solutions, yeah? Maybe you show there are no complex solutions, well, then there are no real solutions, yeah? But in this case, even there are real solutions, yeah? But the solution is not positive definite, give me a Riemannian magic, yeah, but semi-Riemannian, yeah? Not Lorentzian, even worse, yeah? Signature like whatever, yeah? Some signature, yeah? So then we do not know any methods, yeah, saying like there are no real solutions in this subset, yeah, of positive definite matrices, yeah. Yeah, I mean, it is really this. I mean, I always say this, yeah. If you could prove this thing, yeah, homogeneous plus Ricci flat implies flat, I'm dead sure this would have tons of applications, yeah. Even so, this looks like, well, so what, yeah. And this is really estimates, yeah. It's really about estimates, yeah. Which, yeah.
Okay, other questions? All right, so I think we can thank Christoph again. Thank you.